Alrighty guys, here I'm going to talk about some special examples, or I guess problems that love to reoccur when you're talking about forces. First thing I'm going to do is I'm going to talk about what about if an object is sitting on a table being pulled by a rope upwards. And how does that change things? Well, what that's going to do for me overall is that's going to play with my force normal. So let's make a couple of assumptions here. Let's say the object's moving at a constant velocity and that the object is touching the table right there. It looks like it's floating a little bit. So what can we say here? The first thing we're going to say is that if the object's moving at constant velocity, what you should be able to immediately tell by that piece of information is that F net on the system is going to equal 0. So the summation of all my forces on this is going to equal 0. Let's draw a free body diagram. We're going to have, from our center, we're going to have weight. Upwards, we're going to have force normal. To the left with the table, we're going to have friction. Now, you can draw friction from the center of mass or from here. Technically, here's more correct, but we're ignoring torque or any momenta potentials here in this question since this is the intro to dynamics. So this is my free body diagram. Oh, this would be also force applied. So force applied, we're going to call this upwards to the right. Now, the second part of any type of question I gave you in class is once you draw the free body diagram, the next thing I want you to do is redraw that, but what I want you to do is include its components. Now, I don't want you to get in the habit of drawing those components on top of your free body diagram. This is a do not touch box. Do not touch. Once you draw your free body diagram, you leave it alone and you redraw instead. So what I'm going to do is redraw my free body diagram and add my components to it. And let's do that. So let's draw my little box. Let's draw my force applied upwards to the right. That's not what I want. Let's draw my force applied upwards to the right. Make sure your arrowheads connect. Got weight, frictional force, and force normal. Here's what I want you to notice is that be able to draw the components of what's going on right here. So I have force applied from the string, or you can call that tension. So this is force applied in the x direction, and then I'm going to have force applied in the y direction. From here, now that I've drawn my components, what I can do now is write out my equilibrium statements. So let's go ahead and do that. Let's see if I can just move this right out of the way. What I can say is that in the horizontal direction is that the summation of my forces, we already said earlier, is going to equal 0. So summation of force in the x direction is going to equal 0. Summation of the forces in the y direction are also going to equal 0. So that means for me, force applied in the x direction is going to equal force of friction. And force applied in the y direction plus force normal is going to equal weight. From here, we could expand upon and try to look at whatever the system is trying to solve for. So say, for example, if we're looking for frictional force, but we know force applied in the x direction, we can use a little bit of our trig magic. So if I redraw a triangle real quickly, and I know this angle right here, from the horizontal, force applied in the y direction, this would be sine. So sine of theta equals force applied in the y direction, all over force applied. So I can use a little bit of math magic here and say force applied in the x direction is going to be cosine theta. Force applied. So real quickly, that just means force applied cosine theta equals frictional force. Now we just talked about the frictional force formula and say it's objects moving at constant velocity, so that could be mu sub k times force normal. Over here, force applied in the y direction could be force applied sine theta plus force normal mass times gravity. Now, if you have this point of the question, usually you'll know enough information to get you into some trouble and solve for whatever you're trying to solve for. So if I'm trying to solve for force normal, you would usually have mass and gravity, force applied, trig magic, help you there. If you're looking at coefficient of friction, you would usually find force normal over here, and then find that. What you can do is you can ask me questions about applications for this specifically, but since we're not dealing with any numbers, this is all that we have right now. What I am going to do is I'm going to show what happens if instead of me pulling upwards, I pull downwards. So if my force applied is now in the downwards direction, we should expect force normal to increase. And that's because since I'm pulling into the ground, if I'm pulling into the ground, that means force normal has to be larger. So what does that look like exactly? Alrighty, so let's do this. Let's take my object. And now let's pull on it in the downwards direction. Force applied in the downwards direction. Draw that arrowhead a little bit nicer. So my free body diagram is going to be just the same. We're going to have weight downwards, force normal upwards, and friction to the left. So the only thing difference between the old example, which was up here, is that my arrow is going to be going downwards rather than up. So anytime you draw a free body diagram in this class, you don't touch it, you move it off to the side, put a little do not touchy box around it, and then we move on. So now let's go ahead and do this. Let's go ahead and redraw my box and include its components. Oh, let's make that box a little bit darker. And so I got force applied. Oop, not a box. I want a line. Force applied. And then we're going to have weight. Force normal. And frictional force. What I can say here now is that since this object's moving at constant velocity, the summation of the forces in the x direction and the summation of the forces in the y direction are all going to equal 0. So with that being said, let's do that. So summation of the forces in the x direction equals 0, and the summation of the forces in the y direction are also going to equal 0. So this tells me we're going to have to use a little bit of trig magic here. Let's break this into its components. I'm going to have force applied in the x direction, but now my force applied in the y direction is going to be going downwards rather than upwards in the previous example. So that means for the x direction, what I got over here is I've got these two forces going in the x direction. So frictional force is equal to force applied in the x direction. And I have two forces going downwards and one going up. So that tells me my downwards force, which is weight, plus force applied in the y direction is going to equal force normal. Frictional force is often going to be mu, this is mu sub k since it's already moving, times force normal. Force applied in the x direction, this would be, if this is my trig triangle, adjacent over hypotenuse, so that's going to bring me cosine of theta equals force applied in the x direction over force applied. So that means force applied in the x direction is going to be force applied cosine of theta. Over here, weight's going to be mass times gravity plus force applied in the y direction. It's going to be force applied sine of theta equals force normal. This is about the most you can do with these questions, and then either going to use one of these two setups right here to help you find out your unknowns. If you need a specific example, let me know. If you got any questions, give me a holler.